Who has questions? We'll start there.
I had some questions.
Okay, we're going to start with Charlotte, then we're going to go to Rebecca.
Okay. On page 109, questions 43 and 44.
Take a look. Oh, same question for each, right?
Yeah, pretty much.
So let's just do a few of one of them.
Okay.
We'll do 44 since it's not in the book, the answers, that is. So I'm going to do a switch share here real quick. So you should be able to see my paper. See if I can get this lined up. So you're supposed to identify the ions in things like this. I'm going to pick an easy one to write out because it's short. So the idea here is that this is a metal and it's going to be a cation. The rest of this is going to be the anion, regardless of what it's made out of. This also means that it's made out of 1 aluminum and 3 OHs. Now, because aluminum is in group 3A, we know that the charge on it is +3. So we can take all of this and we know that the aluminum is +3. And the OHs must have a charge on each one of them so that 3 plus and each of these charges added together equals 0. So I'm going to do a little 3 plus 3 question marks is equal to 0. So 3 question mark is equal to -3. So question mark is -1. Now, no one does all this work. They just go, oh, well, that's a 3 plus, then each of those must be a -1. Now, that's one way to figure out the charges on OH minus, but you should have memorized it anyways. So
I was
the answer
mostly
is,
wondering about A.
what's
on
that?
I was mostly wondering about A on that one.
Well, that's no problem. It's the same process. You know, there's one of these and there's 2 of these. And you know this is 2 plus, so what do each of these have to be?
What, -1.
Yep. Another way we write this is this way. So what is that formula for? It's acetate ion. So that's how you do all of these. The first metal is going to be your cation. The rest of it will be your anion. And sometimes it's polyatomic. Okay?
Mm-hmm. Okay.
All right. All right, Rebecca, go ahead.
I had some problems coming up with the empirical formula on problems 89 and 91. I just couldn't get them to be round numbers. I couldn't figure out how to make it the right ratio.
Okay, so 89 says cumene, a hydrocarbon, is a compound composed of only carbon and hydrogen. It is 89.94% carbon and its molar mass is 120 grams per mole. What are the empirical and molecular formulas of cumene? So let's take you through the whole process here. So this is 89.
Right.
Cumene is 89.94% carbon, the rest hydrogen. Get the empirical and molecular formulas. So let me show you how to get the empirical. When you have percent data, what you do is you find out the percent for each element. So if it's 89.94% carbon, then it's going to be 100 minus 89.94% hydrogen. And that's going to end up being 10.06% hydrogen. So any questions about how I get the 10.06%?
No, I'm with you so far.
Okay. Once you get the percentages, you want to take those percentages and pretend you have that many grams. Because this really means 89.94 grams of carbon out of 100 grams of cumene. And this means 10.06 grams of hydrogen out of 100 grams of cumene. So this means if we had 100 grams of cumene, 89.94 grams would be carbon and 10.06 grams would be hydrogen. We're going to both of these into moles because formulas of compounds don't have masses, they use moles. So I'm going to use 1 mole of carbon. And since I have my book here, I'm going to use 12.011 grams of carbon. So this will allow me to calculate the moles of carbon. And I can see that 12 is going to go into there at least 5 times and probably another 3 for around, well, not 3, but I'm going to say 7.5 times. 89.94. Oop, I made a mistake. And I get 7.488 mole of carbon. I'm going to go ahead and round to 4 sig figs. I think it'll be okay. And here for hydrogen, our book has 1.0079 grams of hydrogen to 1 mole of hydrogen. And we can tell this answer is going to be really close to 10, right?
Yeah.
Oops, I made a mistake. Not enough zeros. And we get 9.981 mole of hydrogen. Now we want to figure out the ratio of hydrogens to carbons, and there's 2 ways to do it. One way is just to do this. And you divide by the smaller of the 2 numbers. So we're going to keep the same ratio, but one of them is going to be 1 exactly.
I just figured out what I did wrong. I think we'll see when you get your
Okay.
answer.
And here we get this, and we want these to be whole numbers, right? So how can I fix this? I can take this whole thing and I'm going to multiply by 3 and get C3H4. 1.333 times 3 is 4.
Right. So I got up to C and 3/4 and H and 1. I just didn't multiply by the denominator to get C.
This part right here?
Yeah, I just put when I divided, I just put
Yeah. So this is one way to do it. Another way to do it is to take these numbers and do this: 9.981 mole of hydrogen over 7.488 mole of carbon. And when we do this, we find out we have 1.33 mole of hydrogen to 1 mole of carbon. And again, these need to be whole numbers. So we would multiply this by 3 and get 4 mole of hydrogen to 3 mole of carbon. let's talk about some other numbers you get. What if you get 1.25? What are you going to multiply that by? 4, right? And what if you get 1.5? What are you going to multiply that by?
2.
2. What if you get 1.66? What are you going to multiply that by? It turns out 3. Because 3 times 0.66 is 2. What if you got 1.20? What would you multiply by? 5. Okay, so those are the things that you need to do here. And just to finish it off, this is the empirical formula. Now, to get the molecular formula, here's what you do. You take the molar mass of the molecular formula divided by the molar mass of the empirical formula to get a multiplier. And the molar mass of our molecular formula, they tell us is 120.2 grams per mole. And for our empirical formula, we got 12.01 times 3 plus 4 times 1.01. I'm just going to round those off. So we've got 36.03 plus 4.04, which comes out to 40.07. And I don't think we need to do a whole lot of guessing to see that that's 3. So for the molecular formula, it's going to be the empirical formula multiplied by the multiplier. So in this case, we're going to have C3H4, and our multiplier is 3. So that becomes C9H12. And if we take this number here and figure out the molar mass of that, 9 times 12 is equal to 98. And is that right? No, that's 108. And 1 times 12 is 12. Add these two together, you get 120, and it checks out. So this is the kind of work you show for the molecular formula. Nice and, well written out, well organized. And this is the kind of work you show for the empirical formula, and that's what's required. So what do you think, Rebecca? Are you going to be okay with 87?
Yeah, I have a question. So if you have 3 elements in the compound after you do all of that work and divide by the largest number, if I have like a number that 2 numbers that are the same, like 1 and 1 number that's 0.4 or something, can I just multiply them by 10 and then reduce?
Yeah, you can do that also. That's another way to do it.
Okay, I'm okay then. Thank you.
So yeah, so that'll work. All right, Charlotte, you said you had many questions. Go ahead.
Number 71 on page 111.
71 on page 111. How you doing, Darlie? Are you okay? You have any questions?
I'm doing good. I'm okay right now.
Okay. What was that? You're a what?
I'm okay.
Okay. You're going to be a wallflower for a little while. Okay.
Yes.
Calculate the molar mass of each hydrated compound. Note that the water of hydration is included in the molar mass. This is pretty straightforward too. I'm going to go ahead and do this copper sulfate pentahydrate. So we have copper sulfate pentahydrate. And let's talk about how to name these guys. So you name it based on the ionic compound. So this is copper 2 sulfate. And I know that because I know that this is a copper ion. I know this is the sulfate ion. And I've memorized the charge on the sulfate ion. And because there's one of each, the copper has to be a +2. And because copper is not in 1A, 2A, 3A, and it's not zinc and it's not silver, I have to write the charge in the name. So copper 2 sulfate. Now, what do we call this? We call this pentahydrate. So those prefixes we learned before are also used here. So that's the name of this compound, copper 2 sulfate pentahydrate. One compound that is kind of weird is this guy. So this is calcium sulfate. And notice there's no parentheses here because calcium's in 2A. We know the charge is +2. So what do we call a half? We call it a hemihydrate. So how are you going to remember hemihydrate? Well, think of the word hemisphere. Hemisphere means half of the sphere. We live in the northern hemisphere if you look at the equator as being the halfway point all the way across. And some people live in the southern hemisphere. I've never lived there. I don't know that I've ever been there. I don't think I have. Okay, at any rate, hemi, the way I remember it is because it's hemisphere, hemihydrate. So rather than do this one, let's actually do this one. So to figure out the molar mass of this, we have 1 calcium sulfate and we have 1/2 H2O. So to figure out the molar mass of this, we have 1 calcium, 1 sulfur, and 4 oxygens. Here we have 1/2 O, and we have 1 hydrogen. So this 1/2 times 2 is 1 hydrogen. This 1/2 times 1 is that. So we actually have 1 calcium, 1 sulfur, 4.5 oxygens, and 1 hydrogen. So the calcium is 40.078. The sulfur is 32.07. The oxygen is 16.00, and the hydrogen is 1.01. I should multiply times. So get 40.078, 32.07. 4.5 times this is 64.72. And then 1.01. Add these all up together and you get 1415, 5, and we round to here because of these guys, the way I've done it. So we get 145.16. So we would say that 1 mole of calcium sulfate hemihydrate is equal to 145.16 grams. And that would be the molar mass. So how would this differ between the two? Here, you'd have 1 copper instead of 1 calcium. Here, you would have 4 oxygens plus another 5 for 9 oxygens. And here you would have 10 hydrogens. So we good on that one?
Yeah.
Okay. So it's really just a little bit more work. And what you can do also for something like that is you could just do H2O is equal to 2 times 1.01 plus 16.00, which is 18.02. So 1/2 H2O would be 1/2 times 18.02, which would be 9.01. 5 H2O would be 5 times 18.02, which would be 50 plus 30, 80.05. So you could say 5 mole of H2O is 80.05 grams, and you could add it to your grand total for the other part of the compound. So that's another way to handle it. Okay, the reason I did it the other way is so that you got a little bit of insight into how to count hydrogens and oxygens in a hydrate. Okay, what else?
Can we do number 75?
No, that one I couldn't do, so that's why I wanted you guys to do it. Isn't it one of your homework problems? Yeah, that one's too hard for me to do. I'm kidding. Let's read it. Sulfur trioxide is made industrial in enormous quantities by combining oxygen and sulfur dioxide. What amount, moles, of SO3 is represented by 1 kilogram of sulfur trioxide? How many molecules, how many sulfur atoms, how many oxygen atoms? Okay. So we're going to take 1.00 kilograms of sulfur trioxide. And we want a lot of things here. We want moles. We want molecules. We want sulfur atoms. We want oxygen atoms. So we need to know a lot about this particular formula. We need to know, for instance, that 1 mole of sulfur trioxide is 6.022 times 10 to the 23rd molecules of sulfur trioxide. And you have to be careful here because I'm using the word mole and I'm using molecules. So we don't necessarily have to use this word molecules. We could just say that, and that'd probably be okay, right? We also need to know that for 1 sulfur trioxide, there's 1 sulfur and there's 3 oxygens, right? From the formula, 1 sulfur, 3 oxygens. Or we might want to use this for 1 mole of sulfur trioxide. There's 1 mole of sulfur and 3 mole of oxygen. I don't know which of these I want to use. We also might want to know that for 1 mole of sulfur trioxide, there's 80.07 grams. And so how did I get that? Well, sulfur is 32.07. Oxygens are 16. So you get 48 plus 32, which comes out to be 80.07. And you also need to know that 1 kilogram of sulfur trioxide is 1,000 grams of sulfur trioxide. So we probably need a lot of these. So let's do A, B, C, and D. So for A, 1.00 kilograms of sulfur trioxide, I'm going to multiply by this guy right here. 1 kilogram of sulfur trioxide over 1,000 grams of sulfur trioxide. And then I'm going to multiply by, to get the moles, I'm going to multiply by this, 80.07 grams of sulfur trioxide to 1 mole of sulfur trioxide. And I can see that this answer here is going to be more than 10, because this will go into that more than 10 times. And it'll probably be more like 12 and a half, right? So how many significant figures are we allowed? 3 because of that. So 12.5. Now for B, I think the easiest way to do that is do the 12.5 mole of sulfur trioxide and multiply by 6.022 times 10 to the 23rd sulfur trioxide for 1 mole of sulfur trioxide. So here, when I think about 12.5 times 6, I know that 10 times 6 is 60. 2.5 times 6 is like 15. So this is going to be 75 times 10 to the 23rd, or 7.5 times 10 to the 24. So I get 7.52 times 10 to the 24 SO3s. Now, since I have that, I'm going to go ahead and go with that. And I'm going to put down, I'm going to use this guy right here where I have 1, 1. And I'm going to actually put 1 sulfur to 1 SO3, which means I'm going to have 7.52 times 10 to the 24 sulfurs. And for oxygen atoms, you can see it's going to be the same, only different. I'm going to multiply by 3 oxygens per 1 SO3. So it'll be this times 3, which ends up being what, 22.5 or 22.5 or 2.25 times 10 to the 25. 2.26 times 10 to the 25 oxygens. Okay, so any questions about that?
No.
Okay. Any other questions? Okay, well, if you don't have any more questions, then let's go ahead and do some problems that I picked out of the back of the book that are similar to the ones we just did. So an Alka-Seltzer tablet contains 324 milligrams of aspirin, 1,904 milligrams of sodium bicarbonate or sodium hydrogen carbonate, and 1,000 milligrams of citric acid. The last two compounds react with each other to provide the fizz, bubbles of CO2, when the tablet is placed in water. Calculate the moles of each substance in the tablet. We're not going to do this for all three. We're going to be doing this only for aspirin because they actually ask a follow-up question on aspirin. But the way you calculate the molar mass for one of these is the way you calculate the molar mass for all of them. So I'm gonna do aspirin. So I'm going to take my 324 milligrams of aspirin, and I'm going to call this ASP. I'm going to convert that into grams of ASP, and then I'm going to convert that into moles of ASP. And for the moles of ASP to go from grams to mole, I need the molar mass of aspirin. So I'm going to say 9 times 12.01, 8 times 1.01, 4 times 16.00, 9 times this is 108.09. 8 times this is 8.08, and this is 64.00. So I add these all up and I get 17 here. 8, 8, and 4 is a 0 plus a 2 and an 8, so I get 180.17. So I know that 1 mole of aspirin is 180.17 grams of aspirin. I could also say that 1 aspirin is 180.17 U of aspirin. So I can use that number for the amount of a mole or the amount of 1. Okay, so I'm going to take the 324 milligrams of aspirin, and I'm going to write 324 times 10 to the minus 3 grams of aspirin. So remember how I said that you can get rid of a prefix by substituting the number for it? That's what I just did. Now I'm going to multiply by 1 mole of aspirin per 180.17 grams of aspirin. And when I think about this number here, I think 180 goes into there almost 2 times. So the answer should be almost 2 times 10 to the minus 3 moles. A little less than 2, so we'll call it 1.7-ish, okay? We get 3 significant figures because of this. So 324 divided by, I'm going to cross that out, right? 324, 180.17, and I get 1.89 or 1.80 times 10 to the 3rd mole of aspirin. So for a problem like this, this is the kind of work I'd expect to see. And I'd expect to see this if I asked you to show me the molar mass calculation. But usually I don't ask you to show me the molar mass calculation, so you better get it right. Okay, next, if you take 1 tablet, how many molecules of aspirin are you consuming? Well, I'd go ahead and start with this, 1.80 times 10 to that, and that's supposed to be negative 3 mole of aspirin. times 6.022 times 10 to the 23rd aspirin per 1 mole of aspirin. And you can see this number is going to be pretty big. This number here is going to end up being around 12, 1.8 times 6, not 12, maybe 10, or maybe 9 point something, and then times 10 to the 20. So times 6.022 second EE23 ends up being 1.08 times 10 to the 24 aspirin molecules. Oops, 21. Sorry. 22. No, 21. So when you think about this aspirin tablet and you think about how many cells there are in the human body, and let's say that there's I don't know, an outrageous number, 100 trillion cells in your body. So that's this number divided by 100 trillion. So trillion is, that's billion, that's trillion, and we said 100 trillion. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That would be 1.08 times 10 to the 8th aspirins per cell. That number is 108 million aspirin molecules per cell. And I don't think our human body has 100 trillion cells in it. I could be wrong. But one little tablet and you're getting millions of aspirin molecules per cell. So imagine if you take 2 aspirin tablets. Oh my goodness. You're just asking for it. Okay, so I don't think people quite understand just how small molecules are and why the medications you take are good enough for your whole body. It's because you're getting millions and millions of molecules in each cell. Any questions there? Are you guys kind of impressed with that? No, you're not impressed? You can say yes if you're impressed.
I'm impressed.
You should be. Y'all should be. Okay, let's take a look at another problem here. Calculate the mass percent titanium in the mineral ilmenite, which is FiTiO3. So to calculate the mass percent, it's going to be the mass of the part over the mass of the whole. So if we want to calculate the mass percent iron, we would calculate the mass of iron over the mass of iron, titanium. So this would be what you'd calculate. And I forgot, you're going to multiply by 100% to turn this into a percentage, because otherwise you just get a fraction. Okay, so here we're supposed to calculate the mass percent titanium, not of iron. So the mass percent titanium would be the mass of titanium over the mass of FeTiO3 times 100%. So I'm going to work my way across here so that we can see the work. The mass of titanium is simply the mass of titanium in the book. And so for titanium, we have 47.87 grams. And what I'm going to do here is we have 1 iron, we have 1 titanium, and I'm going to cross that out. And I'm going to actually write we have 1 mole of iron, 1 mole of titanium, and 3 mole of oxygen. and iron is 55.85. So we have 55.85 grams of iron. Titanium we just saw is 47.87, which is 47.87 grams of titanium, and oxygen is 16. So that's 48 grams of oxygen. When I add all those together, you can see that that plus that is about 50, plus that is about 150. So let's see what we get. Okay, so I get 151.72, and this is good to the 10th. So here I've got 47.87 grams of titanium to 151.72 grams of this iron titanium oxide times 100%. And we can estimate that this is going to be about 33%. And I get 31.36% titanium. So this is kind of the work you'd expect to see for that.
I got
Yeah.
31.55.
What's that?
I got 31.55.
Maybe I
Wondering
put my
why.
wrong, maybe I put my numbers in incorrectly. Let me
Maybe
check.
it's good.
31.55, yep. Okay, so let me show you how to do this second part, because this is the way I'm going to want to see it on a test. What mass of ilmenite in grams is required if you wish to obtain 750 grams of titanium? So you'd write 750 grams of titanium, and you'd multiply by 31.55 grams of titanium per 100 grams of ilmenite. So the idea here is what I've circled in there means that 31.55 grams of titanium is equal to 100 grams of ilmenite. That's what 31.55 means. It's 31.55 grams out of 100 grams, or 31.55 pounds out of 100 pounds, or 31.55 ounces out of 100 ounces. 31.55 means out of 100. And so when I write it this way, I realize that I can use either side on top and either side on the bottom, and I can find out how many grams of iron or ilmenite that I'm going to need. And you can see here, since percentage is defined as 100, this is exact, this is 4 sig figs, this is 2 sig figs, so we're allowed 2 sig figs. When we look at this, we'll go into that about 3 times, and 3 times that is about 2250. So let's see what we get. And I get 2.4 times 10 to the third grams of ilmenite. So that's the way I'd expect to see that. And if you did something like this, and got 2.4 times 10 to the third grams, which answer is better for getting to here? This one or this one? And clearly this one is better, because you're showing how you're converting grams of titanium to grams of ilmenite. Secondly, you're showing that your answer is grams of ilmenite. Here, it's grams of what? I don't know. So this is what I would call insufficient to receive full credit, or even close to full credit. I mean, this is, no one knows what the hell's going on. This, everything's labeled. You get what's going on. So you're good to go.
Well,
Any
Tony,
questions there?
if we put the grams of Fe, I forgot what the compound was called. If we
Aluminum. Go ahead.
put that behind it, it would still be the same ratio, like 1 aluminite molecule to 0.3155 grams titanium. If we still put the units behind, would that be fine?
Put the units behind what?
The fraction 1 over 0.3155.
Yeah, but when you have this, you shouldn't be turning it into a fraction. That the definition of percentage means out of 100. So you should be saying 31.55 over 100. That's what that means. And so when you move the decimal over, you're polluting it. This is taking that and doing that. Why bother when it's all going to work out the same? I know it's a different mindset because your math teacher says, oh, just move the decimal over 2 places. Your math teacher wasn't doing you a favor. Your math teacher was not teaching you. You should use 31.55 over 100 or 100 over 31.55. Just get used to it, okay? All right. So math teachers usually teach you really good stuff, but I hate it when they teach you tricks. All right, we're going to move on. An organic compound has the empirical formula of C2H, that's a 4, NO. Its molar mass is 116 grams per mole. What is the molecular formula? So this is the one where you take the molar mass of the molecular formula divided by the molar mass of the empirical formula. What is the molecular formula of the compound? And you get the multiplier. And then you take the empirical formula and use that multiplier to figure out the molecular formula. So here we've got the molar mass of the molecular formula. And they don't make this clear. When they say the molar mass, they do mean the molecular formula. So we've got 116.1 grams per mole. And for C2, H4, NO, you got times 12.01, which is 24.02, 1.01, which is 4.04. This should be times 14.0. I want to say 1, but I'm not sure. Yep. And then we've got times 16.00. You'll notice all these numbers that I'm using are basically good to the 100th because the periodic table that I give you on the test is good to the 100th. So trying to get you kind of used to doing that. Okay, when we add these all up, we get 0.07. And this adds up to 30, 34, and then 58, I believe. So 58.07 grams per mole. And here it doesn't take a genius to see that that goes into that 2 times. So our formula becomes C2H4NO with a multiplier of 2, which becomes C4H8N2O2. And there is your molecular formula. Any questions about that? Okay, we're going to move on then.
I did have a question about just the periodic table on the exam.
Yes.
So since we can't like switch windows through Proctorio, is it going to be something we can like print off ahead of time and get used to? Because right now the periodic table I'm using has more significant figures than the back of the book, just because I struggle with looking at the computer screen.
What I usually do is I put a periodic table with every problem.
Okay.
So you'll have that with every problem to look at, so you can scroll up and down. Okay.
Yeah, sounds good. Thank you.
And usually I put it at the top of the problem, and then you read the problem below the periodic table. Although I'm not sure if that works better to put the periodic table at the bottom.
So will it be the whole periodic table or just a section of it?
It'll be the whole periodic table.
Okay,
The whole thing with the symbol, the atomic number, and the molar mass. But
Okay.
the symbols will not have names below them. And I can't remember if it says group numbers in it or not. Let me see if I can find it real quick and I can show it to you, okay?
Yeah, I was also wondering if you, while we're on this topic, if you had any more information you could give us about like the format of the test, like short answer or calculation problems.
It's
how many
it's
problems?
all short answer, which I consider calculations also to be short answer.
So do you have any idea, or can you tell us about maybe how long the exam? You said it's timed, and how
Ele-
maybe how many
11
questions?
problems, and you get 2 hours and a half to do it.
Okay, thank you.
So that's what, 150 minutes divided by 10, that's 15 minutes per problem,
And it'll
Which
probably
should-
take that long.
which should be plenty. The way it's going to go is you're going to spend 5 minutes on each problem and do 8 of them, and that's 40 minutes. And then you're going to have 3 problems where you spend half an hour on each of those, and that's your time. That's the way it usually works. You know, there's always a few that you can't do. Okay, so I'm looking up that periodic table. Here we go. I believe this is it. Maybe that one isn't it. Hang on a second. Hang on a second, people. Okay, let me close this and open this other one up. Where is it?
Tony, are we allowed a calculator on the exam?
Absolutely. So that's a yes.
Thank
Okay.
you.
So, yeah, because absolutely, you don't know what the heck I mean, right? You bet. You bet your bippy you're allowed a calculator. So do you see this periodic table? Did I do my share correctly? I think I did.
Yeah,
So-
we can see it.
So you see how the symbol of the element is there? And the atomic numbers in the upper right-hand corner, and the molar mass or atomic weight, whatever you want to call it, is at the bottom. Now, you'll notice that the columns are not labeled 1A, 2A, 3A, 4A, so you better know that. These are named in the more standard way, where you just call them 1 through 18. So you better know that the towers are the A's and the wall are the B's. So probably this periodic table. Okay. So I'm going to close that now. I'm going to go back to my share. So let's do this here. Complete the following table. I don't know that we need to do this one. Empirical formula, molar mass, molecular formula. Here, how do we do problems like this very quickly? We take the molar mass of the molecular formula, divide by the molar mass of the empirical formula to get a multiplier. And then you take the empirical formula and you use that multiplier to get the molecular formula. So in the case of this, we would have a molar mass of 150 grams per mole. And for this formula, we've got 24 plus 3, which is 27. And 27 plus 48 is, see, 27 plus 48 is 75. And here you can see you get a 2. Now, you'll notice in all the problems we've done so far, the multipliers have been whole numbers. And if you don't get a whole number, it's because your data is a little corrupted or because you screwed something up big time. So you should get close to a whole number. You might get like a 1.8 or maybe a 1.9 if your data is a little corrupted, meaning not perfect, but you should get close to a whole number. You should not get something like 1.5. Any questions there? So in this case, you would have C2H3O3 to C4H6O6. Any questions on A? So B would be the same route. In the case of B, though, I can tell already that the molecular formula is also C3H8. Sometimes the molecular formula and the empirical formula are the same. Okay, and you can imagine how to do this one, right? What is the empirical formula of this guy? B2H5, right? Because empirical is the simplest ratio. 2 to 5 is simpler than 4 to 10. Why can't we do this? Why is that no good? The answer is you can't have fractions as part of your formula like that. Okay, let's move on. So here's another one of these. A poisonous compound found in tobacco leaves is 74% its molar mass. What are the empirical and molecular formulas of nicotine? We're not going to do that one. We're going to skip to something that we might come back to that. But I want to do something a little more exciting, and that's this one here. Elemental sulfur is combined with fluorine to give a compound with the formula SFX, a very stable colorless gas. If you have isolated 5.722 grams of SIFX, what is the value of X? So let me show you how you tackle a problem like this. So we're talking about sulfur here, and it's not a Honkelbrief. And we know that it's a solid at room temp because the gases are hydrogen, nitrogen, oxygen, and all of those. We've kind of memorized those, right? It's combined with fluorine, and that's a gas at room temp. And it gives you this formula, SFX. Now, we're not trying to balance this. We don't care about the numbers in front. And I'm saying that because you've had a chemistry class before. You know about coefficients. You know how to balance things. How do I know this is a gas? And I simply know this is a gas because of this. It says it's a gas. Okay. Now we start off with 1.256 grams of sulfur, and we end up with 5.722 grams of this stuff. So this is the beginning. Now, what we should know is that whatever amount this is, and I'm going to call it Y grams of F2, we know that if we add these two numbers together, they should give us this number. So Y grams of F2 is going to be 5.722 grams of SFX minus 1.256 grams of S. So I can see that the difference here is going to be about 4.5, right? So let's see what we get. 5.727, and correct me if I get the wrong number here. 1.256.
It's
And
5.722.
What's that?
It says you've isolated 5.722 grams.
Oh, I didn't make my 2 very good, did I? So we get 4.466 grams of F2. Okay, so we know that we've got 1.256 grams of sulfur and we've got 4.466 grams of F2, and we could calculate the mass percent F in this and the mass percent sulfur in this, right? Says to calculate mass percent, you would take the part divided by the whole. So we could get the percent sulfur is equal to 1.256 grams over 5.722 grams times 100%. And we could get this. So 1.256 divided by 5.722 times 100, which is 21.95% sulfur. And so the percent F, I'm not even going to worry about F2. The percent F is going to be 78.05%. So how do I get 78.05%?
100% minus 21.95%.
Right. Now this is a waste of time. Because the idea here is that, well, if I had that, I could say, you know, this times this many grams times 1 mole per blah. Don't even need to do it. What we're going to do is we're going to take the 1.256 grams of sulfur, multiply by 1 mole of sulfur to 32.07 grams of sulfur. And we're going to get the moles of sulfur in here. And 1.256 divided by 32.07. And I should get a number less than 1, probably even less than 1/10. And I get 3.916 times 10 to the minus 2 mole of sulfur. Now I'm going to take my 4.466 grams of F2 and multiply by 1 mole of F2 per, so I'm using the formula F2 here. And I get,
Should we only use the percent calculation way when given the percents?
yeah, because this is an extra step you don't need.
Right.
So the point is you can calculate the formula from mass data or from percent data.
Right.
You use the percent way when you get percent data and use the mass way when you get mass data. Now, this one's a little tricky. I'm going to tell you that right now, 38.00 grams of F2. And this is tricky because you have to multiply by 2 mole of F to 1 mole of F2. Because we don't want moles of F2 over here. We want moles of F. Okay, now I'm going to show you another interesting thing though, and that is this. We could also multiply by 4.466 grams of F and not assume we have F2, but that we have F times 1 mole of F per 19.00 grams of F, and we're going to get moles of F. I want you to take a look at these two calculations and see what is different about the two. Not the beginning number. These are different, and this is different. Well, how many times does 2 go into 38? 19. So do you see that you get the same result either way? So my point is that when you get to something like this, we don't have to say F2. We can just say F and not have to bother with the 2 mole of F per F2. Okay, let's see what we get. 4.466 divided by 19.00. And I get 2.35 times 10 to the minus 1. Now I'm going to be honest with you. It might be easier for you to do something like this, 0.3916 and 0.2351. Whoops, 1, 2, 3, 5, 1 times 10 to the minus 1. To see which number is bigger, right? Which number is bigger? That one. So I would do this then. Sulfur 0.3916, another 0 there. Fluorine 0.2351, and divide them both by the 3916. So I get sulfur 1 and fluorine divided by 3.916 second EE negative 3, 6.5. If I did this right. And so we get that it should probably be S2F13, if I did it right. That seems like a weird number. I'm going to be honest with you.
So when you divide by the smaller one? I thought it was the bigger one.
Oh, you always divide by the smaller one. That way, one number ends up being 1 and the other number ends up being greater than 1, because you cannot have a formula where it's less than 1. So if you divide by the bigger number, you're only going to get one number being 1 and all the rest are less than 1. And that's probably why you want to multiply them all by 10.
Yeah. So
Yeah.
I should do it the other way.
Yeah, divide by the smallest. That way, that one ends up being 1 and the others end up being bigger.
Okay.
And when they end up being bigger, you get things like 1.33, which you multiply by 3, or you get 1.5, or you get 3.01, or you get, nice numbers to look at, in my opinion. I like them all to be bigger than 1, but I like one of them to be exactly 1. So you see how this one's exactly 1 and this one ends up being 6.5. Can you have a formula that's like that?
No.
No. So what's the most reasonable thing to get that to be a whole number?
Multiply by 10.
I could multiply by 10, right? But then what would I do?
Simplify.
Divide everything by 5, right?
Yeah.
And I'd get that. I'll be honest, I don't think they wrote this problem correctly because I've never heard of this compound. Let me make sure I wrote down the numbers correctly. Wow, I did. And this is correct. And it makes sense that this is going to be a lot bigger than this, right? Because that's 4 times bigger than that, and this is half the size. So this should end up being 8 times bigger than that, which it is. And it's 6.5 times bigger. So this is an interesting compound I didn't know about. All right, so what have you learned from this problem? The big deal here is if you have masses, use masses, for goodness sake. Okay, this is a problem that we'll just talk about briefly. And the idea here is, what is the term allotrope mean? So allotrope, this is a particular physical form of an element. So here we've got oxygen and we've got ozone, O2 and O3, different forms. You've got carbon, which is diamond, which is carbon, and you've got graphite. These are both carbon. A lot of elements have different forms. Phosphorus, you've got red phosphorus and you've got white phosphorus. And you can well imagine that these things all react a little bit differently because of their forms. So that's all an allotrope is. You don't need to memorize allotropes of anything, but I do want you to be aware of that word allotrope, which sounds like isotope. But allotropes are the same element, but different physical forms. Any questions about allotropes? Okay, there being none, let's put this down. So this is another one of those ones we've done before. How many moles, how many atoms? I don't want to do that one again. Let's take a look at this one. So, there are smart ways to do things, and there are, and when I say smart, things that save you time and get you the right answer. And then there are slower ways to do things. So here, which of the following samples has the largest number of ions? Okay, notice it's 1 gram of each. So what is the number of ions going to depend on for each of these? Well, let's just do one of these. If we have 1.0 grams of beryllium chloride times 1 mole of beryllium chloride per, and if we look up the formula here, chlorines are 35.45 and beryllium is 9.01. So if we add all this up together, you get 551, carry the 1, 91, and you get 79. So 79.91 grams of beryllium chloride. And this has the largest number of ions, and there's 3 ions per 1. Actually, I'm going to write this times 3 mole of ions per 1 mole of beryllium chloride. Now, how do I get 3 moles of ions from this formula? And the answer is, if I have 1 mole of this stuff, I actually have 1 mole of beryllium ion and 2 moles of chloride ions, because I got 2 there. So how many moles of ions total? 3. Okay, so if we do all this work here, you can see we have 1 times 3 over. Okay, so we want the largest number of ions, right? So is it clear to see that the more number of ions you have in the formula, the better? And is it clear that whatever the molar mass is, since that's in the denominator, you want a small number here. So you want small and you want large. So let's take a look at the rest of these formulas. How many ions are in each of these? So how many ions here? 3. How many ions here? 2. Oh, that's no good. How many ions here? 2. That's no good. How many ions here? 2. That's no good. But that's not enough. So let's look at their molar masses. The molar mass of barium sulfate, you look at barium and you say 133 and you go, oh my, that's a huge molar mass. And only 2 ions, that can't be it. You look at strontium. Strontium's got a molar mass of 87. That alone is bigger than that. So you go, okay, that's going to be a huge number. And there's only 2. It can't be that one. Calcium sulfide. Calcium is around 40. Sulfur's around 32. So that's 72. 72 is certainly smaller than that. So that sounds good, but it's not much smaller. And there's only 2 ions. So that's the clear winner. And here, when you look at magnesium chloride, a magnesium is bigger than a beryllium. So the molar mass is going to be bigger than that. So your answer is there because the other ones just don't quite fit. So if this were like a multiple choice test, you would just simply say A without doing all the calculations. Okay. All right. So thinking smart.
So you only have to do those calculations other than finding the molar mass or estimating if the amount of each compound is different?
Yeah, so for me, I don't usually put questions like that on an exam. I make it clear that you need to do some calculations and you should be able to figure out what those calculations are very easily. But I don't usually do something like that where you would have to show 5 calculations. It's ridiculous. Okay, so let's take a look at these ionic and molecular compounds. What's the name of this guy, and this guy? Well, this one, is it ionic? So we're actually doing this. Which are ionic and which are molecular? Is this ionic?
No.
And the answer is yes. How do you know?
Barium's a metal.
Barium's a metal. Is this one ionic? No, because silicon is not a metal. And chances are, if it's a non-metal, or excuse me, metalloid, it's going to be a molecular compound.
Okay.
And so that's one of the traits that we did not write down for metalloids, is that they're usually in molecular compounds, but they usually are. How about this one? Is this ionic?
Yes.
Yes.
Yeah, because nickels and metal. So we want to give these names based on whether they're ionic or not. So we're going to start with this guy, which is not ionic, and we're going to call it silicon tetrachloride. Any questions there? So how do you name this guy? Do we need to use Roman numerals for barium? And the answer is no, because it's in group 2A. So this would be barium fluoride. Do we use prefixes for ionic compounds? No. This one, do we need parentheses for nickel? And the answer is yes, because it's not in 1A, it's not in 2A, it's not in 3A, and it's not silver, and it's not zinc. So this is nickel what? Nickel blank bromide.
Is it nickel 2 because bromine is -1?
That's right. So nickel 2 bromide. All right, which has the largest mass? 0.5 of which one? And the answer, or excuse me, 0.5 moles of which one? Well, clearly we have the same number of molecules of each, right? So what's going to have the largest mass is the 0.5 moles of the biggest one of these. So let's look at barium. Barium's 137. Fluorines are close to 20. So 20 plus 20 is 40, plus 137 is 177. Okay. How about this one? Silicon and chlorines. Chlorines are 35.5. So two of them is 71. Four of them is 141 or 142. Plus this, 142 plus that makes it 173. So these are pretty close in mass. You with me there? Now, here, nickel and 2 bromines. Bromines are 80, so 2 80s is 160, plus nickel is close to 60. 180 plus 60 puts it at 240. So this is about 170, this is about 170, and this is 240. Which has the larger mass when you have the same amount of each? This guy. You with me?
Mhm.
So I didn't even do the calculations. I kind of did them in my head. And you know, thinking smart, you know, these are the kind of questions you might see. I would expect to see on a quiz, you know, which has the larger mass. Oh, I just have to do a quick little dirty calculation.
So if we saw that on a quiz, it would be okay if we didn't like write it all out.
Yeah, well, I don't know why you'd write it all out. You could, but you could also just do it quickly. Now, how are we going to do this one? Your choices are to use percentages or use masses.
Percentages out of 100 grams. Sample,
So how many grams of carbon do we have?
22.88 grams,
Right. How many grams of hydrogen?
5.76,
And how many grams of arsenic?
71.36.
Okay. And let's face it, isn't using 22.88 grams a lot better than using 0.2288?
It is.
And here, half the people in the class, if they turn this into a decimal, they'd make it 0.576. And that'd be wrong. It's 0.0576. You know, I really don't like moving the decimal over. I think it's the silliest thing in the world.
Yeah, I'm working on it.
Yeah, I mean, your math teachers didn't do you a favor. And I should have been telling them, why do you guys do this? But you know what? I've seen what they do in algebra. They spend like 12 weeks out of 15 doing parabolas. And when have you run into a parabola since then? I don't even deal with parabolas. Why would they spend so much time teaching me about parabolas? And I'm going to tell you why.
Yeah, I wonder instead of like lines that model data or something.
What's that?
I wonder why, like what a parabola, would be useful for other than throwing a ball up. And
Exactly. Parabolas are great for engineers. It's great for engineers. So algebra is being taught for engineers, not for people who go into the grocery store and buy bananas and want to know how many pounds of bananas they can get if they have $5 in their pocket, you know? And I think that's a mistake. And that's what's turning, I think that's what turns a lot of people off to math, is because you're learning stuff that just has no application. But you can say the same thing about chemistry. Okay, so let's take a look, and this is going to be our last problem because we're running a little long here. So let me show you how you would start this problem off, and I'm going to let you do it on your own. So loom, to find the value of X, you heat the sample of compound to drive off all the water and leave KAL. So this is what's going on here. I don't even know how to pronounce this name. My guess is you'd call it potassium aluminum sulfate. And then of course, if X were 1, it'd be monohydrate and so forth and so on. So when you heat this, you get the dehydrated alum. So this alum, when you heat it, this is driven off. And the way we show that is this way. So they're no longer together when we put a plus sign between them. Is that clear to everybody? So we have 4.74 grams of the alum, and you lose 2.16 grams of water. And I'm going to be honest, this is not the way you normally get the information. How do you measure water that's driven away? And the answer is, well, you have to collect it somehow or other. Usually you're given this number because it's a solid and you have to calculate the water. So normally you would be given that this is a 2.58 grams and you'd have to calculate the water. That makes more sense because you heat this up until there's no more water left. Let me ask you a question here. How would you know there's no more water? No more H2O to be driven off. How would you know?
I mean, after a certain amount of time, you'd stop collecting more water.
Well, the water is steam. How are you collecting it? And the answer is you're not. Like if you were to put this in your oven,
Right.
how would you know that there's no more H2O coming off? I'll tell you the answer. It sounds silly, but this is what you do. You heat this really hot and you leave it in your oven for half an hour, right? Then you let it cool down. And you put this in a test tube because you don't want to mess with it. You don't want to have a powdered form that you keep moving around. So you put it in a test tube. You put it in you weigh the test tube with this stuff in it, but you know how much, you should know how much this stuff weighs and how much the test tube weighs. So imagine you put this in here and you got 4.74 grams and you know your test tube weighs 30 grams and total it's 34.74 grams. What's the likelihood of your test tube weighing 30 grams? Almost zero. I'm just using that number because I can add them. So you heat it and you let it cool down and you weigh your test tube. And let's say that it weighs 34.00 grams. Have you lost water? It used to weigh 34.74 grams. Now it weighs 34. Did you lose water?
Yeah.
Yeah. How much? 0.74 grams. Now you take your 34.00 grams, you heat it, and remember it used to be 4.74 grams. You heat it, and now you get 33.74 grams. Did you lose more water?
Yeah.
Yeah. And then you heat this 33.74 grams, you cool it down and it's 33.75 grams. It looks like it gained weight, right?
Yeah.
Do you see how you haven't lost more water? The weight has basically stayed the same.
It leveled out.
Yeah. So I call it heat to constant mass. once you've made it so that the weight doesn't change, you're not going to lose any more water. So if you, in this particular case, start out with a 30-gram test tube and you start off with 34.74, what they're saying is here, you'd end up with a 32.58 gram test tube with compound. And to get the weight of this stuff, you subtract the 30 grams of the test tube, you get that. Okay, so how do we get the water here? It's 4.74 minus 2.58, which is 2.16 grams. So that's how you get the water. You don't weigh the water first. So this is bass-ackwards. Now what do you do with this information? So let me show you what you do with this information. What you do is you take your 2.58 grams of KLa SO42 and you get moles of KLa SO42. You take your 2.16 grams of H2O and you get your moles of H2O. And then what you do is you take, I'm going to call this X and I'm going to call this Y. You take your X moles of H2O over your Y moles of KAl SO42, and then you simplify this. And you want to actually make this a 1, so you divide both of these by Y. And so here, if you get like 0.521 mole of H2O, and you get 0.261 mole of KAl SO42, that comes out to be 2 mole of H2O to 1 mole of KLAl SO42. And therefore, the formula is KAl SO42 to H2O. So do you get the idea here of what we do? So
Yeah.
to give you some nice directions on what you do here is you take the mass of the ionic compound formed and you get the moles. You take the mass of the H2O and you get the moles. And then you take the moles of H2O over the moles of ionic compound to get the ratios. And that's it. Sound pretty easy?
Yep.
Okay. Because I think this is going to be your next lab for tomorrow. Well, you're not going to use the alum. You're going to use something else. Something in your kit.
So I had a question on stuff that we should be memorizing.
Yeah, go ahead.
So I know that we should be memorizing those polyatomic ions.
Oh, yeah.
Should we also be memorizing the ones you mentioned, like the binary molecular compounds you called them? The propane, ethane, methane, phosphine, ammonia?
The common names, don't worry about those right now. You will learn those when we get to chapter 23.
So I should pretty much just be remembering the fixed charge polyatomic ions of that sort.
Yeah, and the variations. So for instance, if you know
right, the H variation and the 8.
the A-type variation.
Or whatever. Yeah.
So, yeah.
That was a little bit confusing to me.
The best way to remember those is the chlorate. So take a look here. Chlorate is this one, right? So from this one, you should be able to get 3 others. So there's chlorite, 1 less oxygen. And 1 less oxygen is hypochlorite.
I mean, could it also be phosphate, and phosphite is one less?
Yep. Yeah. Sulfate, sulfite.
Okay, and you can do that to any of the polyatomic ions.
The answer is no. And the reason I say no is that some of them don't have the ite. They just don't exist. But I will say this,
Okay,
if it does have the ite and you know the 8, you're gold.
okay,
Okay, they all follow this trend if the ite exists.
and it's just adding or subtracting an oxygen.
Right, but the charge stays exactly the same. So
Oh.
here, see this guy here? This one's called bromate. Can you figure out what bromite is?
BrO2.
Can you figure out what BrO minus is?
Hypoborite. I don't know.
Hypobromite.
Oh, bromite.
Yeah, hypobromite. And what is BrO4?
Perbromite.
Perbromate.
Perbromate. Okay, so you
Right.
pretty much just need to memorize that variation.
Yeah, so if you know the 8, you should be able to figure out the rest. So one more oxygen, the 8 stays the same and it's perbromate. One less oxygen, the 8 becomes an ite, and one less oxygen, it still is an ite, but it's a hypo.
Okay.
So do you see how the ones with very few oxygen are the ites, and the one with more oxygens are the 8s?
Right.
So that's the big difference. And of course, which has more oxygens, ite or hypobromite? Well, hypo means less, right?
Right.
And which has more oxygens, bromate or perbromate?
Perbromate.
Per, because per means hyper, which means elevated.
So then with the H plus variation, it keeps the charge the same and just.
Oh no, the charge does not stay the same. So here's the perfect example.
Oh, I see that. It actually changes the charge. So the charge stays the same for the 8 and ite variation and changes for the H variation.
That's right. And you'll notice that the charge becomes less negative the more hydrogens you have. Less negative.
Okay. Right, because it's adding a +1.
Correct.
All right.
So the most common ion that's like that is this guy right here. And this is called hydrogen carbonate. And I'm sure your high school teacher said, oh, and that's called bicarbonate. Which is really interesting because bi makes you think there should be 2 hydrogens, but there's not.
Yeah, I think the example you gave of dihydrogen phosphate, and then the one after phosphoric acid, how would we ascribe the H variation to something other than phosphorus?
Well, this is hydrogen carbonate, right?
Right.
This is carbonic acid. So why are there only 2 and there's 3 here? And or I should say H3PO4, which is phosphoric acid. Why are there 4 here and only 3 here? And the answer is this guy starts with a -2, that guy starts with a -3. So this guy gets an extra 1 because of the charge.
Okay.
Does that make any sense?
Yeah.
So I'm going to show it to you a little more slowly. You see that?
Right.
Add a hydrogen, becomes a -1. Add a hydrogen, and it becomes neutral. Because you start at a -2, there's only 3 things here. But if you start at a -3,
Okay. Right.
you
Right.
get a -2.
So you just bring it down until you balance it at the acid.
Yeah.
Okay.
And it turns out that you're going to have to memorize these formulas of these acids. And if you know this, that actually tells you how many hydrogens you're going to have in the acid.
Is that something for the future we'll have to
Oh,
memorize?
yeah. So knowing these polyatomic ions means you're going to be able to know those acids also.
Okay.
So this is carbonic acid. This is phosphoric acid. Sulfuric acid.
Okay.
Those are the biggies.
And that's just adding enough hydrogen to balance the polyatomic ion charge.
That's right.
Okay.
And that's how they actually form.
All right. Thank you.
Okay, well, we're way over. So that's good. We covered everything that I wanted to cover today. Tomorrow, look for the lab. You're gonna need the, you have a little bag of sulfates. You're gonna need the test tubes. You're gonna need an oven. You're gonna need an oven. You could try it in the microwave. I've never tried it in the microwave before, but you can give it a try. I'll give you directions on what to do. All right. Okay, thanks for coming, everybody. Turn on your mics, say goodbye to everybody.
Bye, Tony. Bye, everyone.
Hope to see you guys tomorrow.